All right, you ready, Chris?
I guess as ready as I'll ever be.
Okay. So I'll introduce you and then we'll get started. So today we're very happy to have Chris Kapulkin talking about a cubical setting for discrete homotopy theory. So take it away.
All right, thanks a lot, David. Thanks for having me. It's a great pleasure to speak in the Topos Colloquium. So I'd like to talk about something that may be a little bit surprising. So I want to talk about graph theory, shockingly, and I'm not a graph theorist. I'm not doing any kind of combinatorics, and so it's been a strange journey for me this whole time. But yeah, I want to tell you about that. And before I start, I just want to say that all the new results presented here are joint work with Daniel Carranza. And so Daniel was an undergraduate student here at Western, and it was a great honor supervising Daniel. So I remember watching this comedy show in which a comedian said that, you know, like he had this one day when he learned all the swear words, and until then he only had these things as a raw feeling, and once he learned all the swear words, he could finally tell people how he feels. And supervising Daniel was kind of like that. He had this incredible potential. He had all those contributions he could make. All I had to do was teach him some swear words like anodyne extension or a Kahn complex. And yeah, so Daniel is here, but I think he has to go at 2 teach. So I'm just going to say, if you have any hard questions, I prefer that you ask them now so that he can answer, because I can only answer easy questions. Okay, so that's my preamble, and let me now move on to the actual content of my talk. So what I'm going to be talking about is a homotopy theory in the category of graphs, and I need to describe that category. So what is the category of graphs? It's a category that I'll denote graph, and its objects, perhaps unsurprisingly, are graphs. And for me, these are undirected without multiple edges, so simple, I suppose, and without loops. And so I can view a graph as just a pair VE, where V is just a set of vertices and E is just a subset of 2-element subsets of E. And now there will be also maps, and graph maps will be maps on the set of vertices, such that whenever I have an edge from V to W, so this is edge in G equal GE, then one of 2 things must happen. So F of V, again, there's an edge between them in V prime, or F of V is equal to F of W. So there are many different ways of looking at this category. You can look at it as a reflective subcategory of some presheaf category. You can look at it as a category of graphs with loops, and then every vertex has a loop on it. There are many, many ways. And so let me give you a few examples of graphs that are of interest to me and are important for this talk. So the first one is what I'll call IN, the interval of length n, which will be a graph of this form. So it's 0, 1, 2, all the way up to n, like that. Okay, that's a graph. You can also you can also identify this point with this point, and that's the cycle. So this goes 0, 1, 2, 3, and n minus 1, and then to 0. So that's another graph that you may be interested in. And here's one more, I infinity, which is the graph that has 0, 1, 2, and so on as in, but also you can go in the opposite direction and have negative numbers. So sometimes this graph could be denoted z. Okay, and one observation to be made right away is that this graph is nothing else but the colimit of I0 into I1 into I2 into and so on, except I need to be a little bit careful in how I construct these embeddings because if I kind of just always pick the initial segment, I'm not going to get the negative. So that means I need to alternate left embeddings with right embeddings. So if I start here with, let's say this is 0, 1, this one is 0, 1, 2, and then this one will be 0, 1, 2, 3, then the first embedding, maybe here, we'll take this to this edge, but then the second embedding, I will take this thing and embed it at this graph over here so that I keep adding. So, great. So these are a few examples that you may be interested in for one reason or another. And of course, we want to make new graphs out of old graphs. So one good method is to come up with some sort of monoidal product. So here's product of graphs. So if I have two graphs, let's say G, which is VE, and G prime, V prime, E prime, I can construct their product, which I'll denote this way, which is not the way it's usually denoted by people doing graph theory, but for reasons that are important to me personally, I prefer this notation. So it has vertices. The set of vertices is simply the set of vertices of V and vertices of V prime, and edges. Well, there is an edge from V prime to W prime, if and only if V is related by an edge to W and V prime is equal to W prime, or V is equal to W and V prime is related to W prime. Okay, so that's my notion of graph product. And let me just quickly do an example. So let's say that we want to find out what the product of I1 with I1 is. So if you think about it for a second, it's a graph that will look like this. Okay, so it will be a square, which maybe tells you something about why cubical sets may be relevant in a second. And one observation that I'll make before moving on is that this is not the categorical product. The categorical product. So the category of graphs is a reflective subcategory of a tree-sheaf category. Therefore, it has all limits and co-limits. And in particular, you can see that I1 times I1 would be a graph that looks like this. Okay, so the diagonals are there, and this thing is too small. Okay, cool. So let's just record that although this is this product is not the categorical product, it is a monoidal product nonetheless. So the category of graphs with this product and I naught is a closed symmetric monoidal category. And in particular, you can construct this product as a reflection of a certain deconvolution product or that exists on the preshift category, of which this is a reflective subcategory. Okay, great. So once I define product and something that looks like an interval, I'm just one step away from doing homotopy theory. So here is the definition of homotopy. So a homotopy between two maps, F and G, from graph G to G prime, is map H from G, this funny product, with IN, such that, well, H restricted to maybe, okay, let me just say this H restricted to G tensor 0 is F, and H restricted to G tensor N is G. Okay, and needless to say, I can now define homotopy equivalences. So a homotopy equivalence is a map F G G prime such that there are, well, G going in the opposite direction and homotopies from GF to identity on G and FG to identity on G prime. Okay, so let's try to figure out what graphs are up to homotopy equivalence. Like that's how we do things in homotopy theory. So a few examples that may be instructive. So we have a map from the cycle of length 3 to I0. And this map happens to be a homotopy equivalence. And it's very easy to construct the inverse. The inverse actually requires a one-step homotopy. So the inverse just embed at any vertex, right? And then in order to show that the constant is homotopic to the identity, do the only possible thing. And this happens to be a graph. Okay, so the 3 cycle is contractible. So if you came to this whole thing thinking, well, that's going to work just like for topological spaces, why do I need to listen to this guy with thick Polish accent? The thing is, I mean, I can't do anything about the accent, I'm sorry, but it doesn't work exactly like it does in Hatcher, right? For Hatcher, the 3 cycle would be not contractible, it would be S1. But for us, the 3 cycle is contractible. Okay, so let's go C4 to I0. And this again is a homotopy equivalence. How can we see that? Well, now we cannot contract everything to identity in one step, but a 2-step homotopy. So the fact that we, in our homotopies, allow this n to vary is important. So we have a homotopy like that. And essentially what you're doing is in the first step, you're going to contract those 2 vertices like that. And once you have this, you're going to contract this vertex here. So let me not go into the details here. Maybe I'll just say that as we look at this as 0, 1, 2. So here I'm describing the transformations happening to C4 as we move along I2. Okay, so now you may think, okay, so the cycle. Oh, yeah.
Quick question, Chris. You had us quite short here at the University of Augsburg with that example. Is there a functor from the category of graphs to the category of topological spaces which preserves homotopy equivalence so that we can make pictures of graphs as they are intended to be regarding homotopy?
That's a great question, and I'll answer that. Essentially, you need to hear the rest, and then.
Okay, we're looking forward to it. Thank you.
No. So yeah. So if you want the answer, I'll give you the the answer, but yeah. Okay. So C3, C4, great. And now let's move on to C5. And so this map is not a homotopy equivalence. Okay, and we will see that in just a second. But in essence, what's happening is that C3 and C4 are very, very small cycles. So they're too small for us to see that they are empty inside. But once we get to C5, of course, now we can clearly see that there is void inside, void that we cannot fill. And in fact, more is true. So Cm is not homotopy equivalent to Cn for all Mn greater equal 5 and M not equal to N. So cycles are very, very different from the point of view of our notion of equivalence. Okay, and the last thing I'll mention is that also I infinity to I naught is not a homotopy equivalence. So, so why is that? Well, if there was a homotopy contracting the whole infinite line to a single point, well, this homotopy would have to be of finite length, but but I infinity is, well, infinite. Therefore, we cannot contract. Okay, so that's nice and hand wavy, but how can we see, for instance, that this thing is true? So for that, we need to develop some invariants, and these invariants are known as the homotopy groups of graphs. Groups of graphs. Okay, so what are homotopy groups of graphs? Well, for a pointed graph, and by a pointed graph, I mean the only thing it could possibly mean for a pointed graph, so a graph with a distinguished vertex, we define its homotopy groups, and these are denoted A1 up to, well, A1, A2, and so on. But let's start with A1. So this is just maps from I infinity to F, sorry, F to G, such that F of N is equal to V naught for almost all N. Okay, and then I need to take these maps and quotient by the notion of a path homotopy. So I can also, let me just remark here that I can also can take maps IN to G instead, since these have any content only on a finite piece, and then if there's any shifting, I can always adjust it using this homotopy over here. However, in order to define then the relation, I would need to pad those maps because I would need to define homotopy between maps of different lengths. Therefore, it's easier to do it with I infinity. Okay, and more generally, I can define AN, the nth homotopy group of a graph, by taking I infinity and its nth tensor power and taking maps into G, such that F of N is equal to V naught for almost all N. So that, and again, I need to quotient here by homotopy. Okay, So one thing that one usually shows in situations like that is that if F is a homotopy equivalence, then the induced map on ANs is an isomorphism, and that holds here. And an interesting theorem that will then let us compare different ANs, or rather different graphs, different cycles, is that, sorry, I want to compute A1, but I want to compute A1 of a different cycles, so based at 0. Well, this group is trivial if k is equal to 3 or 4, and it's z if k is greater or equal than 5. Okay, and so this in particular shows that the 5 cycle won't be contractible, although it does not exclude the possibility that higher dimensional cycles are still homotopy equivalent. But in any case, from this immediately we see that C5 won't be homotopy equivalent to the point. Another observation to make is that we have a map from Cn, another observation to make is that if M is less than N, then, well, there's no surjective map from Cm to Cn. So all maps Cm to Cn induce 0, 0 on A1. And so that's it. Cm cannot be homotopy equivalent to Cn. Oh, sorry.
Chris, are those A1s, A2, and so on, are these groups or sets?
These are groups, yeah. So, what happens is if you have one path, that's probably easiest to see if you, instead of considering maps from I infinity, you consider maps from IN. You can take IM, IN, stack them together, get IM plus N, and this gives you an operation that's
okay.
Yeah.
Like with the fundamental group.
It's exactly, yeah, the topological case works exactly the same. Yeah.
Okay, thank you.
Yeah. Okay, so what we see here is that there is no homotopy equivalence between Cm and Cn. However, it's also easy to see that I have a map from Cn plus 1 to Cn, which is given by f of I equal to I if I is less than n, and 0 if I is equal to n. And this gives iso on all homotopy groups. So maybe I'll just say ANs. So I won't go into the details, but that's what this map does. And therefore, what we see from that is that all CNs for n at least 5 will be weakly equivalent, weakly homotopy equivalent, in a sense that there is a map that induces isomorphism to all homotopy groups. However, they won't be homotopy equivalent. So if you subscribe to some algebraic topology point of view, the cycles are not CW complexes. Okay. The last thing I'll mention, which may not be immediate, is there are graphs with the fundamental group that is not free. So let me just do one example just to explain to you what happens. So this example, you can find it in a paper by Bob Platz, which I'll refer to later, but also there's an argument entirely graph theoretic due to Udit, who's here. So if you have questions about this example, you can 3, 4, 5. Okay, and 1, 2, 3. 1, 2, 3, 4, 5. Okay, great. And then what I'm going to do is I'm going to identify this with this. Oh, what have I done? And this with this. But on this end, I'm going to go in this direction and this direction. And on this end, I'm going to go in this direction and this. So I'm taking this grid and I'm identifying the opposite ends. And I can take the A1 of that based at 0, and this group ends up being Z mod 2. And the way to see it is that this thing pretends to be RP2. If you just take the grid, it's just a disk. You can glue 2 such disks along the boundary, and then when you take the quotient, you get RP2. You take the quotient of S2 by the Z mod 2. And this whole thing is part of a general theory. So, so there is a whole theory of these things, So there are things like covering spaces for graphs, covering graphs really, covering graphs, Van Kampen theorem, homology, lots of things were developed, and I'll try to give some references. But before I move on, I should probably justify one thing, and that is, why the hell are you talking about that? Let me try to explain. So for me, this is just fun, but there are people who also do it for other reasons, and so this whole enterprise really goes back to Atkin, who in 2 papers from 74 and 76. So that was a long time ago. It's a statement. Use this kind of theory to model networks. And the way he did it, networks using simplicial complexes. Atkin defined a homotopy theory of simplicial complexes. So here is a nice simplicial complex. And it was a homotopy theory that essentially studied different simplices and took them as points, and then there was an edge between 2 simplices if they shared a simplex of 1 dimension lower. And so this simplicial complex can be translated to the graph. Well, this, which is exactly C5. And to understand connectivity, to understand things about those social networks or communication networks, it was important to understand A1, for instance, of this graph. And so that's the origin of the story. And more recently, a number of authors, I don't want to miss anyone, so I'll just say that I think it's fair to say that the effort was spearheaded by a fellow Canadian, Barcelo, who is the deputy director of MSRI, and a few other people whose papers I benefited a lot from reading, include Eric Babson, de Longeville, Laubenbacher, Weaver, Kramer, Green, lots. I'll mention some of these papers. But other applications include things like hyperplane arrangements, where hyperplane arrangements, matroid theory, and time series analysis. analysis. And let me just mention that for a great survey of those, you should really read the paper by Barcelo and Laubenbacher. Okay. So from 2005. That's a great survey. And Laubenbacher in particular is a biologist. So we're talking about the theory that's it's not, you know, it's a theory with serious applications. Okay, so now I'd like to understand how we can possibly compute these homotopy groups of graphs. Like, do we need to like just guess them, or like, is there a method of doing it? And let me, for that, let me follow a paper by CBC by, I just want to attribute these ideas properly. So Barcelo, Kramer, Laubenbacher. That's a long name. Tweaver. So here is the observation. Here's an observation that they made. So given a graph G, construct a CW complex XG by taking the one skeleton is G, really viewed as a one-dimensional CW complex, but then glue in a 2-cell for each 3 and 4 cycle. And they prove that if you take then pi1 of this graph, or of this topological space, then this is the same as A1 of the original graph. Okay, so that's great. And that confirms our computations of CNs, of pi1 or A1 of CNs, since yeah, if you look at the CW complex for higher cycles, there will be nothing to glue it. Okay, but the higher ANs are more mysterious. And so higher ANs, well, these are more mysterious. And in particular, it is perhaps unclear whether there is something in whether they are non-trivial. So in 2020, so it's a very recent result, LADS proves that there are graphs with non-trivial ANs or arbitrarily large N's. And the way he does it is in the first step, he constructs the Hurewicz homomorphism like that. So there is something called graph homology. So he constructs one of those things. This is Hurewicz map. And he shows that for many G's, this is surjective. And finally, uses the fact that graph homology, HN, the graph homology is easier. And maybe I'll explain that in a bit. And so in particular, there are non-trivial elements in higher homology groups, and therefore by surjectivity, there will be non-trivial elements. Okay, but what we really would like to understand is whether there is a higher dimensional analog of this statement, right? Of the statement that pi1 of some space is equal to A1 of G. So is there something that we can say about pi n? And the relevant conjecture here comes from a paper by Babson, Barcelo, de Longueville, and Laubenbacher, from 2006, I believe. And let me quickly say what this conjecture asserts. So this conjecture notices that graph homotopy is very cubical in its nature. So let me quickly remind you what cubical sets are. Cubical sets are the best thing ever. And so that's how I got into the whole thing. So I did quite some work on cubical sets in the past. And so I then learned that apparently there's a conjecture in combinatorics related to cubical sets. And I thought, well, how come there's a conjecture that I don't know about? So here's what cubical sets are, just a very quick refresher. So cubical sets are presheaves on the cube category, and the cube category is the category that has as objects posets of the form 1 to the n, where 1 is, that's what I would call 1. And the morphisms, so unlike for, the case of simplicial sets, the morphisms are more restricted. The morphisms are generated by special kinds of maps. So there are faces. So a face map takes a sequence like that, xn, and inserts epsilon at spot I. So you can take a sequence and get a longer sequence by inserting epsilon. Here, epsilon is either 0 or 1. There are the generacies. So when you take a sequence, you're allowed to drop an element from the sequence. So I get a drop xi. And finally, there are connections. And so connections, what they allow you to do is to either max or min two elements. So you take xi, but two consecutive elements, I, xn, okay? And so there's also the min operation. And you need connections for a well-behaved, to get well-behaved homotopy. So maybe, I think there were some talks before in the Topos Colloquium on cubical sets. And so let me just remark that these cubical sets differ from cubical sets that you may have seen because there are no diagonals. So I have no way of doing something like this. I cannot duplicate an element, and I have no symmetries. So no matter what I do, I will never be able to swap two elements. Yeah, the order will always be preserved. And so this is a very well-behaved category. It's just as well-behaved as delta, but as delta is better behaved with respect to join or taking, in simplicial sets, it's easy to take cones, but it's very hard to take products because then you need to triangulate the prism. In cubical sets, it's hard to take joins, but it's very easy to take products. So that's one of the reasons why they could be important in homotopy. And there are two functors that are of, or two adjunctions really, that are of interest to us. So the first of those adjunctions is the geometric realization with topological spaces. So we start with a functor that sends 1 to the power of n to, well, the square, the topological square, which is 0, 1 to the power of n. So it's a topological space. And we can left connextent along the Yoneda embedding. And that gives an adjunction known as the geometric realization and the singular complex, which I'll denote S. Okay, the second adjunction arises in the same fashion, but now we're going to go to graphs. So this sends this fella to I1 to the tensor power of n. And again, we just do the Yoneda extension. And we obtain something that I will call the one realization of a cubical set and the one singular complex of a graph. Okay. In particular, Sing1 of G at level in is given by graph maps from I1 to the tensor power of n into G. Okay, great. So that's very cubical. And the conjecture that those four authors pose is that an of G V naught is isomorphic to pi n as a topological space of the geometric realization of this. So I take a graph, I take its singular complex, and then I take the singular complex and I geometrically realize it. So you immediately see that that's got to be really complicated because I'm doing a right adjoint followed by a left adjoint. So there's nothing good about it. Now, they also prove that if the cubical approximation theorem is true, then the conjecture holds. So cubical approximation is essentially a statement that every map between topological spaces can up to homotopy be approximated by a map, by a cubical map. And one reaction that you should immediately have is, how the hell is that not obvious, right? Like we have simplicial approximation, we have cellular approximation, clearly there is cubical approximation. So go ahead, prove it, be my guest. So every couple of years, someone announces a proof of this result, and very quickly thereafter, we learned that no, it's not actually a proof. And among those that announced the proof and then had to retract it was my distinguished colleague, Rek Jardine. So this is clearly, this is a non-trivial statement, although it may seem plausible. And so now let me just say that what Daniel and I claim to have proven is, first, we remove this assumption. So we don't rely on the cubical approximation property, and we work with cubical sets instead. And I can comment on that. Well, I comment. Like, that's the plan for my talk. So I will certainly comment. But our techniques, our proof techniques, allow us to do more. So we can actually prove the Horowitz theorem. Who knows how to pronounce those Polish names, really? Horowitz theorem for all graphs. So we not only prove surjectivity, we actually prove an isomorphism. And I mean, I'm looking at the clock, and of course, there's no way I'll manage to say anything about that. But maybe if you let me talk a little bit longer, since I got so many questions, I can sketch the proof. Sorry, I'll just make one quick comment, and that is that we recently had this professional development session for our students, where we had a number of faculty come and say how to prepare a good talk. And the most important piece of advice was always finish on time. And I realized I never finished on time. I consider myself the greatest hypocrite that ever lived. So remember, students, always finish on time. Okay, so let me quickly tell you how we prove this theorem. So the idea of our proof is exploit the model structure on cubical sets. Exploit model structure on cubical sets. Okay, so in order to define this model structure, I need to introduce some notation. So the first bit of this notation is I will write cube n for the representable, represented by 1 to the n. Okay, now this fella has a special subobject, which is its boundary. So this is this is the subobject without the identity. Okay, so yeah, so at level n, I'm removing one thing, and then I can also have another special subobject, which is subobject without this and the I epsilon face. So I remove one of the n-1 faces, which is indexed by I and epsilon. So that's the face corresponding to including epsilon at coordinate I. And so these are known as combinatorial boxes. These are known as open boxes. And I cannot resist telling you that this is the worst possible way to open a box, actual physical box. So, okay, so moving on, there's a theorem due to Czesinski. Again, who knows how to pronounce those Polish names? Well, the category of cubical sets carries a model structure. In which the cofibrations are the monomorphisms. The weak equivalences are created by the geometric realization functor. So a map of cubical sets is a weak equivalence if and only if when realizing topological spaces, it induces isomorphism on homotopy groups. And finally, vibrations are what's known as the confibrations. And these are things with the right lifting property with respect to open boxes. So whenever you have an inclusion of that form, X, Y, F, yeah, so you have a map from the open box into X that you can complete in Y. Then there exists some map here, not necessarily unique, filling in this. And so that's a theorem that goes back to Czesinski's thesis. And a quick definition, we call a cubical set a Kahn complex if the map from X to the terminal object is a confibration. And for Kahn complexes, we can define homotopy groups. So I can define pi n of a Kahn complex, pointed Kahn complex, to be more precise, as a map. Well, I'm going to take maps from cube n that send all of the boundary to the point. Oh, sorry, I swapped my brackets somehow. Okay, x naught. So these are homotopy classes of maps. I can do homotopy in any Quillen model category. And so these are maps from cube n to x that send the boundary to x naught, and I can quotient by homotopy. And one thing to comment on this is that these really form groups, and you can define the group structure using those fillers. I can elaborate on that later on, but in particular, you have, I realized that I wanted to draw it differently. So Kahn complexes sit inside of cubical sets, and you can geometrically realize the topological spaces. And in topological spaces, you can take ordinary pi n's to groups, but you also have those things, and it doesn't take much work to show that this square, or this, I mean, it's a square. This triangle commutes up to natural isomorphism, and the way to do it is first go to simplicial sets compared with things there, and then do this. Okay, so somehow we could try to relate cubical, homotopy. Instead of going all the way to topological spaces, we can try to exploit the model structure that we have on cubical sets and work with homotopy groups of count complexes. But here is a disappointment if you try to do it naively, namely, Sing1 of G is con if and only if G is a complete graph. There's an edge between any two vertices. That's a simple fact you can show. And yeah, so is the fun over? No, it isn't. The fun is very much beginning. The thing is, we need a slightly better functor. So what we can do instead, we can realize that Sing1 is just the first of many functors that we can write. Namely, there's a whole sequence of functors, Sing1 into Sing2 into Sing3 into the colimit of those, which I'll call Sing, and this is the colim of Sing-n's as n ranges over natural numbers, where Sing-k G at level n is graph maps from ik to the tensor power of n to G. So in other words, it arises from a different co-cubical object in the category of graphs, rather than given by ik to the I1 to the power of n. It arises from ik. And to see that this is to see what Sing does is it essentially takes maps from I infinity. So maybe I'll just say that Sing of G is at level n is just maps f from I infinity to the tensor power of n into G such that f stabilizes. So I'm not gonna tell you exactly what it means, but you can guess, and also you can just see that this is the colimit. And the theorem that Daniel and I prove is that, first of all, for any graph G, Sing G is always con. It's always con. It's a con complex for any graph G. Two, a n of a graph that's essentially just by definition is just pi n in the sense of a graph of Sing G of V naught. That's by definition. If you just unwind the definitions, that's what you're going to get. And lastly, the map from Sing1 into Sing is a natural weak equivalence. And so we prove this, and with all that, what you can do is you have oh yeah, it's so ugly. You have cubical sets over here. You have count complexes living inside of them over here. Now you put Sing1 here, you put Sing over here, and you have a natural weak equivalence going this way. You can geometrically realize the topological spaces, and in particular, you're going to get going around this way and this way, you're going to get weakly equivalent answers But then when you go to groups, be it by pi n or pi n cubical, this commutes up to isomorphism. Pi n's identify up to isomorphism weakly equivalent topological spaces, and so we're done. That proves the conjecture by working with Hahn complexes instead. So
that's great, Chris. So can I? Are you wrapping up soon?
I'm wrapping up. Yeah, I
Wonderful.
almost wrapped. Yeah, yeah. Yeah. No. So let me just quickly say that. So the way to think about this, really, about this, if you're familiar with this, is Sing1 is kind of like x infinity or x functor for simplicial sets. So that's the functor that Kahn used to construct five-rank replacement for the Kahn-Quillen model structure. And so Sing, this inclusion really is like x infinity. And so the way we do it is when you want to show that something is Kahn, well, since we're humming out of a small object, it factors through some element of the filtration of Sings into Sing1 into Sing2 and so on. And then the combinatorial bit of it is that when you have this admits a map into, so let's see, this is now, do I have the indices right? Epsilon. So if you have something that factors through Sing M, then you won't be able to find the solution to this lifting problem in Sing M, but you will be able to find it in Sing 3M. And okay, so I'll say I'm wrapping up. So corollary, which is the heroic, sorry to mispronounce it. The heroic theorem. Well, this is then so the graph homology, the way it proceeds, the graph homology is defined as the homology in the sense of a cubical set of Sing1 of G with V naught. But this this by homotopy invariants of homology is nothing else but homology of Sing of G V naught. But now this is just you can use the regular Hurewicz theorem to get that this is pi n of Sing G V naught, and this then is a n of G V naught. Okay, so the last the conclusion, maybe let me just say, well, it's not really a conclusion. I think I call it comments, just two final comments. So what we saw is we can really understand graphs up to weak equivalence via this functor Sing, and it really gives us a lot of insight into homotopy groups of graphs. But remember that we wanted to understand homotopy equivalences to some extent versus weak equivalences. And for topological spaces, the situation is very simple. Namely, for CW complexes, they are the same thing. And for fibrant objects, they should be the same thing. Now, here, the cycles are not even, right? The cycles are weakly equivalent, but not homotopy equivalent. So the two could not be further away. So this is something that really puzzles me. And my claim is that there is no model structure for which these are weak equivalences. And I claim that if you want to study graphs up to homotopy equivalences, then the resulting homotopy theory does not even have homotopy limits and colimits. It doesn't even have products. But this, if you want to study graphs up to this notion of equivalence, this carries a structure. These are part of what's known as Brown's category of vibrant objects, part of vibration category, with saying from graph to cubical sets for complexes being an exact functor. So the question is it an equivalence? So this is open. Yeah, if it's an equivalence, that you can realize any homotopy type using graphs. And of course, one thing that we're missing is effective methods of computation, and that's the last thing I wanted to say. So thanks for your attention, and I'll shut up.
Great. Thank you. So are there questions? You can raise hands or just unmute yourself and ask.
Okay, I just had a couple of questions. So that's very nice. Thanks. See people still playing with these. They're great. But some people also study the pre-sheaves with a slight variation on your category, right? Without the degeneracy map, and call that graphs. Is that, have you studied that category much? I guess I missed the very beginning. Maybe you said that at the very beginning.
Here, I guess we're talking about this bit. Yeah, so cubical sets originally were introduced without faces and degeneracies. And I'll say that like the way the cubical sets that you work with are cubical sets without connections. So like one of the insights that I think we have now is that you really need connections to have a well-behaved homotopy theory. So one example of that is in simplicial sets, we know that simplicial groups are automatically concomplexes. In cubical sets, that's not true unless you have connections. So that's one example why you may want connections. The other notion, the other reason why you would like to have connections is that if you don't have connections and you take the geometric realization of the ordinary product of those things, this ends up having homotopy type of S1, which S2, which again is not a desirable property in any homotopy theory. So yeah, so I should say that like the original, so the two homotopy theories are equivalent. They both are equivalent to homotopy theory of spaces. However, working with connections makes things easier. And so, yeah, so I can deduce the result for cubical sets without connections from the result with connections, but it's better to do everything with connections from the start, especially that graphs have connections.
So what I actually meant though was your graph category itself, not the cubical category. So in your graph category, you have two boundary maps, right? Two the head and tail map, and a degeneracy map, and then a switch, right? In your
I'm sorry.
In your pre-sheaf category that you call graph.
Right. So
that one, you have a degeneracy map, right, in there.
Right, but so that's needed to ensure. Where am I? Okay, so I need that map to ensure that this condition is available. So you can consider a bigger graph category in which you don't have that map.
Yes. And people do that because then you get interesting questions like chromatic number. I mean, it's a different category of graphs where you can't collapse it.
Right. Yes. Yeah. So I should say that there are several incarnations of this problem. Yeah, as you say that sometimes I may slightly change this thing. So one thing that Daniel and I were looking at was actually doing homotopy theory of graphs synthetically. So find abstract properties of products that would allow us to reproduce all those results. So different categories of graphs arising from different categories of pre-sheaves, and axiomatize what it is that you need on the monoidal product to prove those results. but this is at very early stages. So.
All right.
Okay,
Anyway,
I think we should probably move on to one more question if there's a quick one, and then we'll stop the live stream. And then anyone who wants to stay on can ask more questions after we do that.
So I can hang out here for a bit. So.
Oh, great. Okay. Any other questions?
Yeah, this might be quick. So I'm wondering why it is better, easier, more convenient to work with cubical sets here as opposed to simplicial sets, which I think you could also map into graphs in a similar way.
Why is it easier? Yes, you can map into graphs. Like this is perfectly fine co-simplicial object.
Or even the complete graphs, for instance.
So that's another option. My intuition, geometric intuition for that, if we're making it a quick question, is this? This is the answer. So when you study homotopies of graphs, you really work with this square, right? Like, because whenever like a homotopy will be a bunch of squares, and a square, it's hard. Like a square can be seen as a degenerate, as a triangle, like just degenerate one edge. But if you know how to build something out of triangles, like it's not necessarily built out of squares. So that's So the fact that it's essentially this thing that we don't have the product here.
So the fact that the square is contractible is really important.
That the square doesn't have diagonals.
Right.
Yeah.
Thank you.
So that the square is not built out of triangles. The building block of homotopy is not, you cannot triangulate it.
Great. Well, let's thank Chris again. Claps in the thing. Okay, and we'll stop the live stream, and anyone who wants to hang out can. So.